Hi, everybody. Welcome. It's October 1st. Welcome to AP Calculus. And we have our check-in question there, so I could double check on attendance. Again, this is AP Calculus. And our quick attendance check-in there in the chat will be, what is your favorite holiday? You could go ahead and put that in the chat. Favorite holiday time. All right, we have Thanksgiving. Okay. Christmas time, Halloween, Christmas, Thanksgiving. Yeah, it's right now what we have is mostly the fall kind of fall and winter holidays. Yep, Halloween, Christmas. Awesome. Good. And Thanksgiving. Yeah, those are so usually I guess the favorite ones are coming up for us then. Halloween, Christmas. I don't know if anyone said anything different, but yeah. Awesome. So let me go ahead and let y'all know who I don't have here, and you could like verify that or correct me if I'm wrong. We got two more coming on in. All right, so this is who I don't have. Welcome everyone who just came in. We're doing our little check-in. Oh yeah, yay, Rosa, thank you. New Year's as the whole family's together, so that's a new one. The common one that people have been saying is Christmas or Thanksgiving. Yeah, New Year's is fun. Oh, birthday or Christmas. Yes, those are good. All right, so this is who I don't have. Kaylin with a C, Kaylin with a K, Fernanda, and Grecia. That's who I'm missing here today. So let me know, or let them know if you're friends with them to come on into class. Otherwise, I'll go ahead and update the attendance. If they come on in, I'll change the attendance for them. So again, that's Kaylin with the C, Kaylin with the K. Okay, cool. I think I got everybody. All right, so welcome everybody. We're here to do some math. Here's our agenda though. We had our attendance and check-in. We're going to take a look at that exit ticket that we did the other day when we were doing the velocity graphs. I liked looking at the data because we had a different amount of answers. So it's interesting to take a look back at on that. Then we're going to take a look and talk about asynchronous number 6, just so we could talk about misconceptions, kind of again like favorite no. Then hopefully today we'll get a chance to actually look at the summative / the mini final. So as you all know, the end of the module is coming up, and it's ending next week Tuesday. So we have Monday and then we have Tuesday, and then that's going to be the end of the module. So again, that's our mini final. It's worth a lot. Basically, if someone has an A and they don't do it, it drops to 2 grades, I believe. So you want to make sure you at least turn in the draft, because then that's not gonna drop it down as much. So that's gonna be like the majority portion of the grade. And as a reminder, we have asynchronous number 7 that's due today. I think 2 of you have submitted that. But I want to say something that later on when we talk about asynchronous number 7 about that assignment, I did add some more to the big ideas packet that will help you out for the mini final. So just as a heads up for those who already did asynchronous number 7, I did add to the big ideas packet. So you could check out what I added. I added like 3 more things, and then that's it on that. All right. Whew, let's go into getting some feedback. All right, so this was the most commonly Missed, not really missed, the most common variety question when we gave out this exit ticket. So the question was, when is velocity highest on the velocity graph? I think that was the question somewhat. You were supposed to like pick a point or like a range of points. And so as you can see, people chose many different answers. We got C, so this point right here. We've got A, this point right here. There's another A, so we have 2 points for A. Velocity is treated from A to B because that's when the slope is the steepest. So someone talked about slope being steep. That's 1 right here. C, because the peak seems to be the highest. So again, we got 2 for C. And I think the velocity is greatest at point A because it looks the most steep and the most positive. So we got 3 here that said A. Increasing would be the greatest velocity. So from 0 to A. So this one's saying kind of like the slope, I believe. This increase is what they're saying, not exactly point A. And then lastly, this answer right here. And again, this is only like a few answers. I just took a screenshot. I couldn't get everybody's answer. It says at point A because it's a velocity V time graph. And we know that the highest point is the highest velocity for that last one. So again, there's a different variety of answers. But yeah, let's go ahead and talk about this. And again, this is kind of like a favorite no. My favorite no here would be that when we're looking at a velocity graph, we accidentally try to see it as a position or a distance time graph. And I believe that's what happened when these 2 students right here, we're talking about the slope, right? We're not looking for the steepness of a slope on a velocity graph unless you're trying to talk about acceleration. When we're talking about the velocity that's the highest, velocity is right here, right? So we're not talking about slopes, or when we're talking about when is velocity the highest. I think the confusion is we're thinking that this is a position or a distance graph. When you have a position or distance graph, then you could talk about the slopes being related to velocity, but this is not the case here. So that would be my favorite no here for those who mentioned the slopes. We're not talking about slopes here. And let me go ahead and clear. Sorry, let me erase this. Okay. So now, whoops, I definitely want to keep the A here. Okay. So yeah, so we're given velocity. And I guess the answer that kind of gets the most information as to why, and basically it's going to be this point. So this point is the most accurate point. The answer that gives the most reason, like the most valid reason as to the why on this, actually there's 2 of them. Well, this one, again, we don't want to talk about most steep because again, that's slope. We're talking about the highest velocity. And they mention it here, the most positive point. It's like the highest, most positive point here on the velocity graph. Down here, the velocity would be negative. And this answer down here said, because it's a velocity time graph, we know that the highest point, which is synonymous with the most positive point, is going to be the highest velocity. So the correct answer is at point A, and it's not going to be a slope. It's actually at a specific point. So this is velocity. The highest, most positive velocity is right here. This one right here would be the most negative, right? This answer would have been correct if I asked you, and I think I did, what was the highest speed? Because remember, speed is the absolute value of velocity. Now this one's magnitude from the x-axis is larger than the one from here. So this one, part C, would have been correct if I asked about largest speed. Because remember, speed is always positive. That's the absolute value. Speed would have been highest here. Speed, highest. So that's a little favorite no. Again, when you have a velocity graph, you have simply that, a velocity graph. If you're being asked what's the highest velocity, you're going to look for the highest point. If you're being asked about speed, Then you take the absolute value of velocity, which would be the positive if it's negative, and so forth. So yeah, so that's my feedback on this one. My favorite no is that we accidentally tend to look at velocity graphs like position graphs or distance graphs. So that's like a favorite no of mine. And again, I call it favorite no because it's, you know, celebrating mistakes, celebrating what we're doing incorrectly, because we learn from them. Let me know if anyone has any questions about this into the chat, or you can unmute. Let me give wait time on that. All right, awesome. I'm gonna go ahead and clear this up and let's move on. So let's see. So this next one that we're gonna talk about as far as misconceptions is, first off, I wanna, before I talk about this part, which is how do we know when an object changes direction on a velocity graph, right? That was also another commonly missed question. What I'm gonna take you back to is this assignment from asynchronous number 3, when we did the moving man. So I actually took this response from what a student, one of you wrote, from your homework on asynchronous number 3. This was the description of what had happened. And the situation was that the man had to go to his house. So he goes to his house right here. He stops. This is the position graph. And then he turns around and goes back to where he started from, which is 0 right here. So he went this way, then he turned around and came back to the starting point. So notice that the position first had a steep incline and then it began to decrease. So the guy started moving towards the house. He stopped right here at this point, and then he turned back around. So his position is decreasing. And when you take a look at the velocity graph, because that's what we're interested in right now, and that question that's going to come up, the velocity wavelength was high. So first, as he was moving towards the house, it was high, but then it became low and negative. So when he turned around to go back to his starting point, notice that the velocity graph intersects here on the x-axis and then goes negative for the rest of the way. So the main idea here is, first off, in a position graph, when you stop and turn around, you see that as a maximum, right? Like a maximum in your graph, like the highest point. That maximum, and let me try to do a straight line here. That maximum should, that maximum should correlate with a 0 in your velocity graph. So that exact point in time when the person turns around, that's going to be when your velocity graph hits 0 on its axis. I don't know if y'all could see that direct thing. It intersects, right? It intersects the x-axis right where the guy turns directions. So he's first moving forward, then he's moving backwards. So the velocity is positive, then it's negative. And at that highest point, the point where he turns directions happens right here where it intersects the x-axis, and right here walking backwards. So the velocity is negative when you're walking backwards, is like basically the key idea. Backwards. Sorry for my messiness. And when the velocity is positive, you're walking forward. So this basically stems from this investigation. And if you didn't do like asynchronous number 3, I definitely encourage it, because then you get to see the actual connections. Like as this person is moving, what's going on with the position graph, what's happening with the velocity graph. We're going to be using this right here that I just saw to go ahead and answer that question that you all had on your quiz. So when do we change direction? So again, if your position graph hits a maximum, that means your velocity graph is going to hit a 0. That's where it intersects the x-axis. Write that down. And then feel free to get this down too. There you go. I should use this more often because I write really messy. There we go. So there's like the main juice of that. And I'm going to go ahead and pause here to see if anyone has any questions about this investigation, about what we notice, about when the change in direction happens and what's happening in the velocity graph when the person changes direction. I just pause and wait. And if we have no questions, I'll jump into talking about the quiz. All right, you wouldn't be able to tell the direction on a speed graph since speed can't be positive, right? On a speed graph, yeah. So yeah, speed can't be negative. That's correct. Yeah, speed graph will always be like above the x-axis. You would not be able to tell the direction on a speed graph. That's why we in calculus and physics, we like velocity graphs because we can see and we could tell when something changes directions or turns back around. So going forward, going backward. We're only talking about horizontal motion, or it could be up and down motion, like water waves or something. Yeah, awesome question. All right. All right, let me go ahead and clear this up. Unless anyone needs me to go back, I think I can undo the annotation. All right, let's go ahead and apply what we just kind of saw from asynchronous number 3. And it's okay if you didn't do this assignment because I basically talked about the main ideas of it, right? Like what happens when you change direction. So how do we know when an object changes direction on a velocity graph? Remember, the velocity graph was that bottom graph we're looking at. And we talked about how it changes direction when it hits the x-axis on the velocity graph. That's just like the main idea from that previous slide. And then let's take a look at what we all said. So a lot of us said A and B. A and B as the change in direction. It was moving forward and the rest of the way it was moving backwards. So I agree, when the velocity graph is above the x-axis, it is moving forward. When the velocity graph is below the x-axis or t-axis, right, whatever it's called, it is moving backwards because velocity is negative. That means moving backwards. But then again, it does go forward up here. So there is some truth here to this first answer. Here it says B to E because it's a negative velocity. Negative means the object is going backwards. Wow, that's awesome. That's an awesome spitting of knowledge right here. So this student said from B to E is when it changed directions. Well, this student is correct that that's when it's moving backwards, but not precisely correct and when it exactly does it change directions, like stop, turn around. Let's see what we have in the chat. And then would C and E be moving forward? Since C and E are still below the x-axis, we're still moving backwards. So let me go ahead and maybe change my color. All of this down here, when velocity is negative, we're always moving backwards. And you could check out that moving man again. Like anytime he moves backwards, you're gonna see that the velocity, it's gonna look like little, like, I don't know, little wavelengths. Like they're always gonna be below the x-axis. So this is always moving backwards when it's below the x-axis. Let's put that down. And velocity graph is below x-axis. It's always moving backwards. And that includes C and E. So from B to E, basically, it's moving backwards and not forward at those points. Wonder if I could change the text color. Yeah, awesome. All right. So again, this one said from A to C, changes after C, it moves backwards from C to E. So this student kind of almost is there, but we're not moving forward from A to C because already after you hit B, you're moving backwards. Ooh, okay, we got particle B. I wish the student kind of explained why that's a location that it's moving backwards, but it is correct because if we're making the connection, when the curve hits the x-axis on the velocity graph, it means we change directions. So that is one of them because it's hitting the x-axis. So we know there's a change in direction. It's going from forward, positive, to negative, backward. This is one of them. And then there's an A again. You could go ahead and read that. Point A. D or E would kind of be particle moving forward or backwards. So that's partially correct if we have D and E. At point A, because it starts to lose velocity, and then A. So actually this was probably the most missed question, right? And again, it has to do with the connections from asynchronous number 3, which is kind of way back. That's why it's good to just bring that back in and talk about it. So again, we're using this idea that we just talked about on the previous slide. So whenever the velocity graph hits the x-axis, it means we're changing directions. So there's another one. It's at B and also at E. That's the specific points and times when we change directions. So the correct answer would have been not from B to E, but B and E. We're changing directions. Let me write that down up here. Not from, on, B, point B, and point. And again, to justify that, it's because you're going from a positive velocity to a negative velocity at point B. So that means positive moving forward, negative moving backward. So you had to change direction here at point B. And then again, you're going from negative to positive. Now you stop. You're going back forward at point E right here. So there's 2 locations. Let me circle this in blue. So the correct answer again would have been B and E. There's 2 points in time when this object in motion changes direction, not A. Oops, yeah, less writing. All right, let me just pause here and see if we have any questions. Questions, clarifications, you can use the chat or you could unmute yourself. Totally okay. Or feel free to just like process all of this as well. Use this time. All right, y'all. Awesome. Let me go ahead and clear all this. Again, I'm happy to also send you all the video later to just rehash these kind of big ideas that we're talking about here. But yeah, let's go ahead and jump into looking at the mini final for this module. But so that was the intention. I wanted us to take a look at the mini final. What you wanted to do is look at your big ideas packet and comment on the summative task based on which big ideas you think you're being asked to use for that question. There's actually 3 parts to it. And the thing is that I haven't posted it yet. And I also know that a few of us still need to look, if y'all are looking at my screen, I think only a few of you did submit asynchronous number 7. Maybe I could have some feedback for y'all. If you prefer to first have some time right now as a class, like maybe 10 minutes, yeah, like 10 minutes to go ahead and try to start asynchronous number 7. Because for those who did do it, I added some stuff at the bottom. I added some more big ideas. You could copy and paste that. So this is a big, huge, big ideas packet. So it's like very thorough. I provide examples. The graphs are from class themselves. Like we talked about these graphs together. I'm using the same examples we talked about in class to help you out. And at the very, very bottom, if you did this assignment already, I added stuff you'll need to know for the mini final, which is all the way down here. I added something called important terms. Something you guys can go ahead and read through that. In the chat, can y'all let me know, do you prefer to first have some time to look at the big ideas packet, then we could transition into talking about the mini final? What works out? You can put big ideas or mini final in the chat, and then we'll go with that. All right. All right, good, good. So far, okay, so far we have big ideas, then mini final. Okay, and then I have a private thing like, what if you already looked at it and da-da-da? For you, I could go ahead and already share the mini final then. I can share it to you. So far, big ideas is winning, unless someone would like to say otherwise. Okay, great. Let's have some time on that. And in addition, it is due tonight. So let's have some time on it. So if y'all remember last year, the big ideas packet, what you're going to do is you're going to read through it. You might need to take your time to read through this. You're going to make a copy. Once you make a copy, you're going to annotate it, right? Like last year by making comments. You're going to highlight and comment. And the goal is to do it on a total of 7 concepts or examples. So remember, if you don't have a question on it, what you're going to do is rephrase your understanding. So if you don't have a question, just rephrase it in your own words. If you do have a question, put your question down. And once you do that, submit it. And then I'm going to return it to you because you need this for your mini final. And I keep saying summative tasks. That's like the summation of all we learned. That's why I keep saying summative, but it's your mini final. All right, so it's agreed that we're gonna go ahead and do this right now. Let's go ahead and take about 10 minutes or so to get started on this, and then we could talk about the mini final, which I haven't even posted yet. Yeah. And let me put the directions on the slide. So just in case. All right, so I went ahead and typed in our directions. Right now, before y'all get started, I need to go ahead and share the mini final for those who are ready. But I'm gonna go ahead and start at about 10 minutes. Let's just come back at 10 minutes. Feel free to just, play some music, whatever helps you to go look through the mini final for about 10, through the big ideas packet for 10 minutes and follow the directions on here. But hold on a second, let me stop sharing so I could give something that a student needs. Let me know if anyone needs me to repeat the directions though. All right, everyone, welcome back. So I'm hoping that we at least got like one or two comments in there, at least getting a start on, it's due tonight. So at least getting a start on it, but I definitely want y'all to see what's on there. Maybe hopefully even skim through it. It's basically all the stuff we were talking about in class. At the bottom, I did put additional definitions you might need actually, you will need for the mini final, is what had happened. So if you go to our Google Classroom, let's go ahead and transition into taking a look at the mini final. So of course you'll have time to finish the asynchronous number 7, finish up your comments, look through it deeply, because this is what you're going to be referencing as you do your mini final. So I went ahead and posted it here. If you go to classwork, it's there organized on what our unit 1 week 3 looks like. So you're going to go ahead, open this, and make a copy. I know it already says copy up here, but go ahead and make a copy, put your name to it. You're going to first just read through this. And what I'd like you to do in the next, let's say 11 or so minutes that we have, let's make it like 10 minutes actually, is just read through it. And as you're reading through this problem, and again, we're going to talk about this, but, and I'm also going to create a support video tomorrow for this. But go ahead and just read through it. And as you're reading something that relates to our big ideas, what I'd like you to do is highlight, make a comment. So for example, I do know like polynomial fit does come up in our big ideas packet. You're going to comment and make that comment so that you know where to reference when you go back to your big ideas packet. So again, read through this, take about 9 minutes, and then we're going to have a checkout question at the end of class. All right. So yeah, we got 2 of us in here already. Awesome. Let's go ahead and all transition here. We're gonna start to make as many comments as we can on what relations we could see from this to the big ideas packet. And for this one, we're gonna have about 9-ish minutes, and then I'm gonna bring us back for our exit question, and also for any follow-up about what's gonna happen, when is this due, so forth. All right, y'all, see you back in about 9 minutes. All right, everybody, welcome back. I hope you got to at least read through it. It's okay if you didn't really yet get to make the comments. Just a few things. Um, so here's the summative test that we're looking at here. Oh, sorry, I think I'm in Swans or something like that. Let me go. There we go. Here's the general one. Oh, okay, I can still see the comment. Okay, so right now, because I was reading through this and I want to make a change in the question. So just so you know, I've been doing this task, creating this task with another AP Calculus teacher. He's over at the SF City Arts and Tech. And I think he meant that this should be 4 times. Change direction 4 times to get 3 relative extrema. So this should be 4. If we all can change that, please. Or I changed it on the original copy, but you're gonna have to make that change. Can you please change this to 4 times? Because then you won't get the 3 relative extrema. And again, the definition to relative extrema is in the big ideas packet, but this needs to be 4 times. If you don't change it, I'm gonna literally go into everyone's copy and change it for you, just so nobody messes up, okay? Because we only have about 17 of y'all in this class, so I could do that. I don't want to trip anyone up, but this should be 4 times, and so forth. So, other than that, as our closing, the closing question and our exit question will be, number 1, what questions do you have about the mini final? Just any question. Number 2, what supports do you think you're gonna need for the mini final? Go ahead and use the chat for that. You could send it to me either privately or you could send it overall so we can all see that. And I'm gonna copy and make a copy of the questions y'all have so that I do address them, for next week when we come into class Monday. So again, it's what questions do you have about the mini final? Or what supports do you think you're going to need for this mini final? All right, so one support that's mentioned to me privately is being able to ask questions when I have about the final. So just being available to address questions. Yes, I could do that. And then another private thing was I just wanted an example of how it should look like. Okay, an example of how it should look like. I could create a video doing an example. Yes. I think I'll need a support video to further explain what's going on or how to even start. Yes, that would be awesome. Are we drawing it on regular paper? Yeah, so basically for part 1, you're going to create a model of the situation that's described right here. So about the mean sea level being negative 62.23, I think that was millimeters. I forget what was the units of that. And by the way, this is from actual sea level data. So that AP Calculus teacher that I'm talking about, he has like a degree in this stuff. So it's kind of cool to be able to actually, get some real life data to apply calculus on it. So just so you know, definitely. And yes, are we drawing it on regular paper? Yes, you're creating a model for the situation that's described there. What I prefer is take a picture of it and then insert it here. That way people can comment on it and look at it when it's time for feedback. A question was, how will you grade it? So this will be graded on like proficiency. So emerging, developing, proficient, advanced. So this will be graded, but the cool thing is you can always resubmit. You can resubmit as many times as you like. Even if this module is done, you keep resubmitting and I'll keep regrading it. As long as you want to improve your grade, you'll get that chance. So that's how I'm gonna grade that. If you don't get it correct the first time, can we try again for some credit? Of course, yes. You're gonna be allowed to resubmit as many times as you'd like. You can also jump into my office hours. I have them at 10 after advisory every day. So totally can also help support there too. But I will be also making that support video that some of you are requesting, and then kind of like do an example. Maybe I'll change the numbers around and so forth so that I could do a related example. No partial credit if we resubmit, right? No, you'll get your full credit. There's no partial credit for late submissions for me. As long as you're learning and you're taking your time to do that, you will get your full credit. All right, any other questions or supports that I should address for you all on this? All right, awesome. So I'm gonna go ahead and make sure I make a copy of all this. Y'all can go ahead and like for now, just focus on getting that big ideas packet, comments down, annotations, get that submitted tonight, and then just rest on it, right? Then tomorrow you could go ahead and take a look at this again, and I'll create some further instructions on this. But other than that, y'all are free to get going. Thank you so much. Again, make sure you get your question in. If not, I'll see y'all later. Bye, everybody. Have a good rest of your day. Bye.